All right, so here is an example of rotational motion and rotational dynamics all in one. You're given this particular graph of angular velocity with respect to time, and then there are four parts color-coded there for you. So part A asks us to find the angular acceleration. Part B asks us to find the angular displacement for the time interval shown in the graph from 0 to 6 seconds. And then part C, we don't really have to calculate. It just asks us whether to determine whether the net torque is positive or negative. And then part D asks us to determine whether angular momentum is conserved. So let's go ahead and knock out part A. Okay. So to do part A, to find angular acceleration, this is pretty straightforward. Acceleration by definition is the rate of change in angular velocity, which is what this graph is omega over time. So we can just go ahead and use kinematics functions or rotational motion functions here. Alpha is equal to omega f minus omega I over change in time. In this case, we're pretty much given everything according to the graph during the time interval shown at 6 seconds. The angular velocity or angular speed here is 0 because it lies on the horizontal axis. And if we trace our graph all the way back to 0 second, you go up. And the initial angular velocity here is 3. So omega f, as I have in the statement, is 0 and minus omega I, which in this case is a positive 3 rads per second. So if you want to do that, it'd be negative 3 divided by 6 seconds, which is a time interval use. And then from there, you can simplify your calculator work to just negative 1/2 rads per second square or negative 0.05 rads per second square. Okay, so that's part A. Now, part B is pretty easy to do as well, as long as you have mastered your linear kinematics. Angular displacement from 0 to 6. So we can just use this particular function from our kinematics. The angular displacement is the initial omega times time plus 1/2 the angular acceleration times the time interval square. So in this particular case, using the graph information, we know that at times equal to 0, the initial angular velocity is a positive 3 because it lies above the horizontal axis. So there's my substitution. Omega I is 3 rads per second. The time interval used here is 6 seconds. There it is, plus 1/2. And then for angular acceleration, we just found on the bottom left of the screen here in part A, which is negative 0.5 rads per second square. And I've gone ahead and substitute that in for you there in the parentheses, negative 0.5 rads per second square. And then the time interval is 6 seconds, but then we got to remember to square that second term there. All right, so if you punch this in your calculator, this 3 times 6 is 18 rads. The second units here cancels out in the first term. And then the second square, and then this s square here being square will cancel out with the s square in the denominator where my cursor is tracing back and forth. And that'll leave us with a negative value because this is a negative angular acceleration according to the slope of the graph. The slope is a negative value. All right, so if you do that, it's simplified down to negative 9, but 18 plus negative 9 yields a positive 9 rad. Angular displacement is a vector, so you do need to include the direction. In this case, the area is above the horizontal axis, as I'm shading out here with my cursor. Because it is above the horizontal axis, it is a positive quantity. Or if you want, you can express it as counterclockwise. That is the accepted direction because we take counterclockwise to be positive and clockwise to be negative. Okay, so if you want, put plus 9 rads, or you can put 9 rads CCW. All right, the second strategy to finding part B, so I'll focus a little time here on part B, is to just go ahead and use the area. From your linear kinematics day. Hopefully you understand that the area beneath the velocity versus time graph is your displacement. Okay, and we can use that same strategy here. This is given as an omega versus time graph, which is angular velocity. So the same information can be pulled. So all I have to do is find the area beneath the slope here relative to the t-axis, and that is my angular displacement. So let's go ahead and shade that in there. I color coded there for you. The area of a triangle is just 1/2 base times height. This one is pretty whack, too easy. 1/2 times the base. Base is 6, height is 3 according to the graph. And if you do that, you will also get 9 rads. Again, I put the positive sign just to indicate that it is a vector quantity. Okay. All right, and then or you can also apply this particular function, average omega is equal to average omega. By definition, displacement over time is your average angular velocity, or you can simply take omega f plus omega I over 2. Now, in this particular instant, we can apply this function here that just came up on the screen because angular acceleration is indeed a constant. So if you look at the graph here, this graph is a nice diagonal downward. It's a negative slope. It's a constant negative slope. So this function can be applied in this instant. So you have to be careful when to apply this, okay? So in this case, it's applicable because the angular acceleration is a constant negative 0.5 rads per second square. All right, other than that, plug and chug. To solve for angular displacement, multiply both sides by t, which is what I've done there. And I use parentheses there just to denote, and hopefully you don't get your calculator error mixed up. All right, angular velocity at 6 seconds is 0. The angular velocity at 0 second, which is your initial frame, is 3 rads per second. And divide that by 2. That's part of the function. And the time interval out here is 6 seconds because I'm looking at the whole entire area shown in the graph. Okay. If you simplify that, you will also get the same value of positive 9 rads per, or just 9 rads, excuse me. And last but not least, this variation here looks like common form in the kinematics function, whereas Vf minus Vi square, or Vf square minus Vi square equals 2a delta x. And again, we've just changed our V to omegas here, our A to angular acceleration, and our delta x into change in theta. If you do that, pretty easy as well. Angular velocity, in this case, in the final frame at 6 seconds is 0. So I put a 0 there. I'm not going to worry about squaring it because 0 squared is 0. And then the initial angular speed, which is 3, is there. I've carried that negative sign down in front of the omega I there because that's part of the function. Don't forget to carry it down. Often it's left out, and then you'll get an opposite answer. Okay, and that's square. And then the angular acceleration that's found in part A is negative 0.5 rads per second square. And then here we are looking for angular displacement. So I'll leave delta theta there alone. Do a little bit of simplification. 3 square is 9. That negative sign where my cursor is at the moment gets carried down. And then this on the right side just simplify down to negative 1. 2 times a half is negative 1. Or 2 times negative a half is negative 1. And then from there, we see that the negative signs will cancel out on both sides. And then 9 divided by 1, which is give us 9 rad as well. Again, the positive sign is necessary since it is a displacement quantity. All right. Now let's do part C. So part C, there's not work to do here. Part C just asks us to tell whether the net torque is positive or negative. So according to the particular problem, the initial angular velocity is a positive quantity. Again, according to this graph, if you go up here at t is equal to 0, angular velocity is a positive 3. So that's where the plus sign comes in. But the slope of a velocity time graph, in this case, the slope of an angular velocity versus time graph tells you the angular acceleration. And to me, this is a negative slope. So therefore, I've drawn here for you in terms of arrows. In this particular unit, we take the counterclockwise direction as positive, which is the omega I direction. And then we also know that from the graph that the slope is a negative quantity, which is your angular acceleration. So here I have angular acceleration is just equal to a negative quantity. And your fundamental kinematics rule, anytime your velocity and your acceleration have opposite signs, the object is indeed slowing down. And not only that, in this case, torque needs to take on the same sign as your acceleration. Okay, so because angular acceleration is negative, your net torque must also be negative as well. So the answer here for part C is your net torque is negative. All right. Other than that, let's do part D. Part D asks us to determine whether the angular momentum is conserved. This one is light work as well. The initial angular momentum is defined as the moment of inertia times the initial angular velocity. And just from the graph, I don't care what I is because we're not asked to calculate. It just asks us to make a statement. Whatever I is, I don't really care. I just carried it down. And then omega I is a positive 3 quantity here. So there's my initial angular momentum, whatever the moment of inertia is, times 3. So determine whether angular momentum is conserved or not, I just have to make sure I can make a comparison. So here's my angular momentum in the final frame, which is at 6 seconds. And then again, here I have I just carry that down because the problem didn't give us mass or anything like that. It just says it's a rotating object. So it can be whatever shape it wants, but it doesn't change the outcome here in part D. And then the final angular velocity is 0 from the graph at 6 seconds. It touches the horizontal axis. So right away, here we have I times 3. Here we have I times 0. So if you're currently awake and thinking that is not equal, I times 3 versus I times 0. 3i and 0 here does not equal. So I've made a statement here. The initial angular momentum is not equal to the final angular momentum. So if you're not whack, you should hopefully make this deduction already that the angular momentum is not conserved. Okay, so that's just using definitions for angular momentum. However, I encourage you to think like this using your linear kinematics or Newton's second law of motion. Here I have recall. It says the angular momentum is only conserved if net torque is 0. In this case, net torque is not 0. So just by looking at this graph, we have an acceleration. And if acceleration is not 0, then net torque can't equal to 0. And because net torque is not 0, the object accelerate or decelerate. So because it's speeding up or slowing down, therefore the object's momentum has to change. Okay, so right away, just by looking at the graph as well, you can also make that same deduction. So here I have the change in angular momentum is defined as net torque times delta t. So for this particular problem, does a torque exist? The answer is yes. A torque exists because your acceleration exists, and the time interval here, of course, exists. So because both of these quantities exist, there must be a change in angular momentum. And if there is a change in angular momentum, we can say that momentum is not conserved. So there's different ways to look at this. Okay. All right. I hope that helps in terms of analyzing part C and D. Just conceptual questions there.